Welcome to our lecture online, and our next topic in our series on thermodynamics is the internal energy of a gas. And to get a feel for what that is, let's go to something that's a little bit more familiar. Let's say we have a rock and we want to talk about the internal energy of a rock. And of course, the internal energy of any object is due to its mechanical its mechanical motion. And so for the internal energy of a rock, it would be equal to the mass of the rock, because if a rock is twice as big, it can hold twice as much heat, the specific heat of the rock, and the temperature of the rock. Well, in the very same way, we can talk about the internal energy of a gas, which is determined by how many moles of the gas that we have, and the molar heat capacity of the gas, and the temperature of the gas. So instead of mass in kilograms, we talk about moles, and instead of the specific heat of the rock, we talk about the molar heat capacity of the gas. And notice the letter V there. The letter V there represents in the situation where the volume doesn't change. So that is the C sub V is the molar specific heat of the gas when the gas remains constant in volume. It can change in pressure, it can change in temperature, but it has to be constant in volume. So then how does that relate to the heat contained in the gas? Because if you just sit there at the gas and the gas is not changing in any way, what's the heat contained in it? Well, we'll talk a little bit more about what this is, because this is an important concept. And the C sub V really depends upon the type of molecule that you're dealing with. For example, if you have a monatomic molecule, monatomic, meaning a single atom in its molecule, monatomic, then the C sub V is approximately equal to 3 over 2 times R. And if you remember what R was equal to, this is equal to 3 over 2 times 8.31. That would be, joules per mole times Kelvin. Okay, so with a calculator, it's 1.5 times 8.31, so 8.31 times 1.5, so it's about 12.5, roughly speaking. So it's about 12.5 joules per mole times Kelvin. And where that comes from is a monatomic molecule has 3 degrees of freedom. It can have translational motion in the x direction, in the y direction, and in the z direction. So typically what that means is that C sub V is equal to 3 times 1/2 R. The 3 represents the 3 degrees of freedom, and since you have a simple monatomic molecule, the only degrees of freedom it has is in motion in the x, the y, and the z direction. And so for all molecules that are monatomic, which is like noble gases, the C sub V would simply be 3/2 R. Now when we do measurements of that, they vary just a little bit, but not by much, so they're all pretty well close to this number. Now, let's say that we have, as an example, let's say we have 5 moles of argon gas at, let's say, 320 Kelvin. What is the internal energy equal to question mark? All right, well, we have 5 moles, so that would be N C sub V times T. We have 5 moles. And might as well write the unit moles down so the units cancel out. 5 moles times C sub V. And remember, argon is a noble gas, which means monatomic, which means it has a C sub V of about 3 over 2 R. So 3 over 2 R times the temperature of 320 Kelvin. Always make sure that the temperature is expressed in Kelvin. Of course, 3 over 2 R is about 12.5 joules per mole times Kelvin. So this is equal to 5 moles. Times 3 over 2, R is 8.31 joules per mole times Kelvin, and then we have 320 Kelvin. Notice that the Kelvins cancel out, the moles cancel out, and we're left with joules, so that gives us 12.465 times 5 times 320, and it looks like that would be total energy contained in the gas of 1,870 joules. So that's how we calculate the total internal energy of the gas. Now, how do we find the change in the energy? Because that's also important. Well, let's say we want to calculate the delta U, the change in energy. So that's equal to, well, let's take a look here. It depends on the number of moles, so if that doesn't change, that's constant. The C sub V for the particular sample of gas that we have will always be the same. And so the only thing that can change the internal energy of the gas is the temperature of the gas. And that's a really important concept. No matter what happens to the gas, the internal energy is only proportional to the temperature. Everything else doesn't matter, assuming the number of moles doesn't change, and of course the gas doesn't change of type, so that the C sub V doesn't change. In other words, the change in internal energy is equal to N C sub V times the change in the temperature. So if now this gas went from 320 to, let's say, 420, a change of 100 Kelvin, then all we have to do is plug in the number of moles, C sub V, the change in temperature, and it'll give us the change in internal energy. If the temperature goes up, internal energy goes up. If the temperature goes down, internal energy goes down. And this is always correct. So make sure that no matter what, you realize that this is always true and correct. Now, what about atoms that are not monatomic? What do we do with a diatomic molecule? Well, for a diatomic molecule, and you can probably think of some examples. For example, hydrogen in the air would be H2 because they tend to combine in diatomic molecules. Oxygen in the air is a diatomic molecule. Nitrogen in the air is the diatomic molecule. So in many cases in the atmosphere we have diatomic molecules. So for diatomic molecules we have additional degrees of freedom so that C sub V is equal to 5 times 1/2 R or 5/2 R. There's 2 additional degrees of freedom because a molecule that's diatomic, which looks like this, can also rotate about the axis like this, and it can rotate about the axis that goes from front to back. So it can rotate in this direction, so you can rotate around the axis like this and around the axis like that, adding 2 degrees of freedom, and therefore the C sub V is equal to 5/2R. And for triatomic molecules, there it gets a little bit more complicated because the structure of the molecules is important. Sometimes we have molecules that are linear, sometimes molecules that are in a V shape. Depending on what shape they're on, they're going to have additional degrees of freedom. But in general, we can say that C sub V is approximately equal to 7 times 1/2 R, with some minor modifications depending upon the shape of the molecule. But that's a good generalization. So we can say that for triatomic molecules, at least for physics problems in general, we can use the approximation that the C sub V for them is about 7/2 R. For molecules that have more than 3 atoms, things get a lot more complicated, and we probably want to go look up the actual values of the particular molecule rather than using the approximation. But it's good enough to say that for monatomic, C sub V is 3/2R, for diatomic it's 5/2R, and for triatomic it's 7/2R. So that's how you can then calculate the internal energy of a gas using this equation right here if you want to know the total energy, and this equation right here if you want to calculate the change in the internal energy of a gas.